Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, yesterday or in the last class we saw the implementation of wall boundary condition, symmetry boundary condition and the periodic boundary condition. Today we will discuss about the implementation of the inlet and outlet boundary condition. Okay. So, we have seen this picture earlier. So, where focus will be today on this pressure inlet, velocity inlet, on mass flow inlet and the different outlet boundary conditions. Okay. So, for incompressible it is slightly easy. So, the implementation of the boundary conditions are different for the compressible flow and the incompressible flow. So, we will look at these flows separately. Okay. So, let us go to the incompressible flow. So, one of the easiest boundary condition that you can implement is the velocity inlet. Okay. So, before you even get into that, you must know one thing is that we cannot specify the pressure and velocity at the same time as the boundary condition, either at inlet or the outlet. Okay. So, if you specify, let us say both pressure and velocity, okay, that is basically over specification. Okay. Why? Because these variables are coupled to each other. Okay. So, if you specify the pressure, the velocity will be calculated from the CFD code to ensure that your whatever pressure value that you are fixed, you are basically honored. On the other hand, if you will specify the velocity, the pressure will be calculated from the CFD code, okay, in such a way that your fixed velocity, whatever value you are giving, is honored, right. But you cannot specify both pressure and velocity. So, that is one thing you must remember, that if you are writing a code, you should not give both pressure and velocity at either inlet or the outlet. Okay. So, in the velocity inlet, if you know the velocity, okay, then you can just provide the velocity there, but in many cases you do not know the velocity. But if by some means if you know the velocity, you can just give the velocity and the angles, okay, maybe alpha and beta, that will be used to calculate u, v and w, okay, the three components, okay, and that is the only thing that you need to specify, and you can get the pressure from the CFD code. Okay. Now, this is used only in incompressible code. Why? Because as you will see that when you go to the compressible code, it becomes an hyperbolic equation, mainly the hyperbolic equation, and then there are waves which will come in through the inlet. Okay. So, that will change your velocity. So, if your velocity is v, and let us say there are some waves which are basically traveling, so that will be v plus v prime. So, you cannot fix the velocity there. Okay. So, the fixing the velocity is very hard in compressible flow, especially at high Mach number. Okay. So, that is why we use this velocity inlet boundary condition for the incompressible code, where we specify all these velocities and the pressure is computed using the CFD code, okay, so which is there inside your domain, and this is good for action dynamics, okay, but you should know that this can only be true when the velocity is sufficiently low that the Mach number is not very high. That means it is nearly incompressible. Okay. So, why it is good for these kind of flows is because you know the velocity of the, let us say, of a car, right, at what velocity the car is traveling, or at what velocity the aircraft is traveling, and so on and so forth. In fact, in the case of car, if you want to simulate flow behind a car, so what you do, so you in reality your car is moving and your road is fixed, okay, and your basically your air velocity is not that high, but the car velocity is very high. Okay. On the other hand, if you want to do CFD simulation, a better approach is keep the car fixed, okay, and give the velocity of the car to the velocity of the air, okay, in the opposite direction. Okay. So, that is one way to basically simulate flow over a car. Otherwise, you have to basically, if your car is moving, then it may go out of the domain, okay, even if you use a periodic domain, then also you have to take care of the moving mesh and so on and so forth, right. but instead of moving the car, you can just move the air. Same is the case with aircraft or the wing. Okay. The other condition is the pressure inlet. Now, this pressure inlet is used for all flows, all kind of flows. It is a general boundary condition. It is available in the compressor flow or the compressor flow. Okay. In fact, in open form also you will have implementation of this everywhere. And why it is general boundary condition? Because the pressure is usually known, right. So, let us say if you have a reservoir here, from there something is coming in. Okay. So, you know this reservoir pressure. Okay. So, this pressure is often called the total pressure P naught or the stagnation pressure Pt. Okay. And from there, let us say you have kept something here for the measurement here. Okay. And this is your window. So, you may not know the velocity here, but you will know the pressure here. Okay. So, that is why the pressure inlet is very common. So, if you want to do the same thing in CFD, you will just use this, use the pressure inlet here and kind of pressure outlet here. Okay. So, in this case we fix the total pressure, which is kind of pressure in the reservoir here or whatever P naught. Okay. You can take this total pressure. In fact, you can use the static pressure also. Some of the solvers you can specify the static pressure also. Okay. In Fluent, specifically you specify total pressure, and it is a better idea to basically specify total pressure than the static pressure, is because you can use this relation easily. So, your P naught is fixed. Okay. And you allow this P n u to vary. Okay. In such a way that your P naught is fixed. Okay. So, you will have some initial condition at t equal to 0, you have to specify some initial condition, and the static pressure will be taken from the previous iteration. Okay. And it also depends on what kind of outlet you have. Let us say at the outlet, let us say you have a nozzle. Okay. And you are putting some kind of back pressure here, right. So, you will the back pressure will also affect the pressure on this side. Okay. Okay, we went to the slightly compressible, but when in the incompressible flow, let us say you have a turbine blade. Okay. And this is the domain that you have. Okay. And the Mach number is very low. Okay. But you have some total pressure here and some static pressure which you call as back pressure here, right. So, this pressure will also affect the domain everywhere. So, you fix the total pressure here and let the pressure on the boundary, static pressure on the boundary P, and you evolve with iteration by considering the back pressure here at the outlet, right. So, it will be basically you will take it from the previous iteration and it will go in the loop. Velocity is calculated using the Bernoulli relation, which is given here. Okay. And this is a sign. So, if you know the P naught, P is taken from your last iteration, you get the velocity of u. Okay. And it is basically keep on recalculated using CFD equation, and this will be repeated. Your total pressure is fixed, but your 2 to 4 will be repeated. Okay. So, this way you will see that as your iteration goes towards the convergence, okay, you will get the static pressure which you expect at the inlet. Okay. So, this is the typical pressure inlet condition for the incompressible flow. Now, you need something at the outlet also. Okay. So, there are okay, before I go to outflow, let us go to the pressure outlet. Okay. So, the static pressure is specified at outlet, as I told you in this example, that you just provide this back pressure at the outlet, and the pressure at the inlet will adjust based on the back pressure. And why we not give the pressure at the inlet also and only at the outlet? Because we want this pressure to be calculated from the CFD, we can only specify either the total pressure or the static pressure. Okay. And once you give the back pressure, if you recall the incompressible flow situation, any information basically instantaneously available everywhere in the domain, right. So, if you have a back pressure at the outlet, okay, it will affect the flow at the inlet also, right. So, you are not basically fixing the pressure at the inlet here. Okay. And this is ignored in the supersonic flow. We will look at the supersonic flow, why it is ignored, but basically you can think of a situation. This is your inlet and outlet, you give a P naught here, use the Bernoulli equation to calculate u. P is taken from the CFD code, and you give the back pressure here or the pressure outlet here. Okay, that is the only information you have to give, and you can calculate all other information using the Bernoulli's equation. Okay, and as the iteration goes and as solution goes to the convergence, you will get your desired static pressure here. Okay. Now you can also compare this pressure inlet with the velocity inlet also. Let us say your Mach number is very low, or the flow is incompressible, and you can try seeing a velocity inlet simulation and the pressure inlet simulation. If you have a good information about the velocity, and you will see that the difference will not be very much at the inlet, let us say in terms of velocity, even if using pressure inlet. But what is very important is that you have one thing fixed and other is floating. Okay, so let us say if you use the pressure inlet, your P naught is fixed. Okay, that cannot change. Okay, that is the boundary condition, it is not changing with time. Your U and P will be changing, the velocity and static pressure will be changing every iteration. If you use the velocity inlet, your the velocity is fixed, that cannot change with time, and the other values will be have to be adjusted, ensuring that your velocity is fixed. Okay, your pressure may change, your P naught may change, and all these things will change if you are using the velocity inlet. So, that is very important thing to understand. Eventually, let us say if you use the pressure inlet for the flow where you also know the velocity, and you got some velocity V, okay, and you did the velocity inlet and got the velocity which is P naught. Okay. So, you will see that this V and this P will be very close to each other, and this P naught and this P naught will be very close to each other, but they will not be equal, right, because you have kept the things floating. So, towards the convergence they will be very close to each other, but they will not be equal. Okay. Sometimes if you want to calculate, let us say you want to calculate Cp, okay, based on your P at the inlet, okay, or the pressure at the inlet, right, and let us say if you have used the velocity or the boundary condition which is velocity inlet, right, then you have to take the average pressure at the inlet to get your P, and then you can use this relation Cp equal to P minus P infinity by half rho U square. Okay, so you know the pressure. So let us say if you have a cylinder here, or let us say an aerofoil here. Okay, so you know the pressure here every point, at every point you need P infinity, which is your free stream pressure. But what boundary condition you have given? You have given the boundary condition of velocity, let us say. Okay, then you have to calculate the P infinity at the inlet. So after your simulation is done, you have got the converged solution. Okay, go back and calculate the average pressure at the inlet. Okay, that will be P infinity, and then you do P minus P infinity by half rho U square. Okay, that is what is your that is how your different inlets and outlets work. Okay, this is for incompressible flow. Another one you can use for the incompressible flow is your outflow. Okay. So in this, what we do, that we set all the flow gradients to 0. Okay, let us say if you have a flow which is like this. Okay. So what are the criteria that you have? That flow should be fully developed. So if you look at how the flow looks like, so because of this step there will be a separation bubble here. Okay, and if you try to plot the velocity, it will look like this, right. So you have a separation region here, and then if you go here, then it will probably look like this, and then it will somewhere here it will become fully developed. So in order to basically apply outflow, you have to make sure that you are going to a region where the gradients are not changing. Okay, you have to go sufficiently far in the domain where the gradients are not changing, then only you can apply the outflow, because by definition the outflow means the flow gradients are 0. So the flow should be fully developed. Okay, then only you can use this. If you are try to use it here, this is wrong. I mean, you cannot use outflow here. So application of outflow is not allowed, okay, here. But if you make the domain sufficiently far, then you can use this outflow boundary condition. Okay. Further, if the flow has got lot of unsteadiness, then also you cannot use this kind of boundary condition in outflow. Okay. So these are some of the boundary conditions that we saw for the incompressible flow: pressure inlet, pressure outlet, velocity inlet, and outflow. Again, this outflow cannot be used with the pressure inlet. Okay. So you can't have at inlet you have pressure and total pressure, and outlet as outflow. okay, because again it creates the pressure difference that you want will not be physical, and that is why you can use this outflow only you have the velocity inlet or maybe mass flow inlet on those kind of bonding condition, but not the pressure inlet, okay, if you are using the outflow. So, these are some of the considerations that you need to take when you are applying the bonding conditions. Now, let us go to the compressible flow. Now, the compressible flow is slightly tricky. Okay. If you say compressible flow, your flow can be subsonic, okay, supersonic, maybe hypersonic, transonic. Okay. There are different regimes, okay, and flow phenomena change depending on which regime you are. And in the subsonic also it can be very low subsonic or high subsonic. Okay, in the subsonic it is typically a Mach less than 1, but let us say Mach less than 0.3. This is low subsonic, it can be comparable to the incompressible flow, or let us say if you are around Mach equal to 8 or something like that greater than 0.8, then the flow can be transonic. Okay. So, what can happen that the flow can be locally supersonic or locally subsonic. Okay, so the specification of one bonding condition, let us say you said okay, give this pressure may not be applicable, because as we will see depending on whether the flow is supersonic or subsonic, the application of the pressure bonding condition matters. Okay. So, the first thing is to determine whether the flow is locally inflow or outflow. Okay, you may have a domain which is this is your inflow or inlet and this is outlet, you know that, but you have to look at locally whether the flow is inflow or outflow, especially if you have a domain which is complicated. Okay, let us say you have a domain like this, then you have to find out whether it is inflow or outflow. So, how do you do that? Okay, so what you need to do is basically you need to find out u dot n, okay, the normal velocity. If the normal velocity is going greater than 0, then it is outflow. This is also called u perpendicular, and if it is less than 0, then this is inflow. Okay. Why? Because this is normal is always outward, right. So, this is a normal and this is u, right. When you say u dot n, if it is negative, that it is inflow. When it is out, so this is u is also going out here and n is also out here. So, u dot n is outflow. Okay. So, you can see the diagram here, this is your n and this is your u. So, this is your inflow because that u dot n is negative, and this here u dot n is positive, right. This is interior and this is outside. Another thing you should see that whether the flow is supersonic or subsonic. So, for that what you need to do, you need to you need to compare your flow at the boundary, basically your Mach number you have to calculate, or you have to basically do a magnitude of u divided by c, okay, which is greater than 1 or less than 1. If it is greater than or equal to 1, this is supersonic, less than or equal to 1, less than, this is subsonic. Similarly, for outflow you have to see whether the Mach number is greater or less than. Okay, because as we will see that depending on what kind of flow you have, your bonding condition matters. Okay, so this we already saw that when u dot n is greater than 0, outflow, less than 0, it is inflow. Okay. Now, what we will do, we will analyze the equations, Euler equations for a compressible flow. Okay. Why we are going to do that? Is because we know that these compressible equations are dominantly hyperbolic in nature, and for the hyperbolic equations, as we have seen when we are trying to find out the characteristic, is that it will have the real characteristic, okay, real eigenvalues. Okay. So, that will give us information. So, eigenvalues are basically is an indication that in which direction the wave is travelling. Okay. So, if the flow is let us say supersonic, your all eigenvalues will be positive, that means all travelling in one direction. If it is subsonic, some may be positive, some may be negative, and then accordingly you have to specify the bonding condition. So, I have written the equations here in the primitive variable form. Okay, these are the Euler equations. Okay, why Euler, why not Navier-Stokes? Is because we are assuming that your boundary is sufficiently far away from where the activity is happening, okay, the core activity is happening. Okay, so that means your viscous effects are not that dominant in that region. You can use the Navier-Stokes characteristic also, but that will become very complicated. Okay. So, there are NSCBC Navier-Stokes characteristic bonding conditions, but they are slightly more complicated, in fact much more complicated, and what people have seen that whether you use Navier-Stokes or Euler, at the boundary, and if the boundary is taken sufficiently far away, it does not matter much. Okay, so we will focus on the Euler characteristic because it is easy to analyze and easy to implement also. Right, so you have this equation del rho by del t plus del by del x rho u equal to 0 and del rho u by del t plus del by del x rho u square plus p equal to 0 and del rho e by del t plus del by del x rho e plus p equal to 0. Okay, this is Euler and also this is 1D. Okay, so we will analyze for 1D equation. Now, the flow may be 2D or 3D, but what matters for this practical implementation is basically your normal velocity u dot n. Okay, so as we saw that gives you whether it is inflow or outflow. So, we will be basically interested in u perpendicular, and then you can make a local 1D assumption there and implement all these equations, right. So, if you expand it, this will become d rho by dt plus rho du by dx plus u del rho by del x equal to 0, right, which is what is written here. Okay. So, you can see this u del rho by del x, okay, this is given here u del rho by del x and then rho du by dx, right. So, this is your first equation. The second equation, you can, for second equation you have to use both the continuity equation, the equation 1 and the momentum equation. So, you can basically expand the momentum equation second one, and you can write u del rho by del t plus rho del u by del t, plus you have to expand this other term also equal to 0, and then you have to subtract this equation 1. Okay, subtract equation 1, subtract equation 1, and you will get an equation which will become du by dt, okay, and plus u del u by del x plus 1 by rho del p by del x equal to 0, okay, which is what is given here by the second equation. Okay. And similarly, for the third equation you have to use E equal to basically kinetic energy plus, so half ui, okay, or half u is coin 1D, okay, and plus CVT, okay, and use those ideal gas equation, and you have to basically use this d rho by dt going to 0, and finally you will get an equation in terms of pressure. So, you please go back and work this out, and you will get an equation which is in terms of pressure. So, right now I have written everything in the matrix form. Okay. So, I hope you know how to read this matrix. We have discussed this also, the matrix form earlier. Okay. So, we have an equation which is d rho by dt, du by dt and dp by dt, okay, and this particular thing we call as matrix A, okay, and we are interested in the eigenvalues of this matrix A, okay, that will give us the characteristic, and these are your velocity. This I am given as the capital U, bold U, okay. So, you can write this entire equation in this form, and if you want to get the characteristic, what you need to do, you need to find the eigenvalues of this matrix A, right. So, your A matrix is given as so you can u rho 0, let me just write it here, u rho 0 u 1 by rho, u 1 by rho, and then 0 rho A square u, right, and you want to do minus lambda is equal to 0, right, and then you have to do determinant of this. Okay. So, not the matrix, but the determinant. Okay. So, you can see this, if you do this u minus lambda, this will become u minus lambda square minus a square equal to 0. It will have 3 eigenvalues, one is u minus lambda equal to 0, that. So, one will be lambda equal to u, other will be lambda equal to u plus a, and third will be lambda equal to u minus a. Okay. So, these are the 3 eigenvalues that you got, and according to each eigenvalue you can now use this eigenvector. So, basically you have to do a x equal to lambda x, okay, and take each eigenvalue, let us say you call it, this is lambda 1, this is lambda 2, lambda 3, right. So, for take u minus a, so put this value 0, let us say if you took lambda 2, let me work this out for you. Okay, if you take for corresponding lambda 2, it will become this equation, if you put lambda equal to u, become 0 rho 0 0 0 1 by rho and 0 rho a square 0, and then you have to basically x, okay, this is your x is equal to 0. Okay, this is what you are interested in, okay, because I have already done a minus lambda I. Okay, I have taken this lambda out. So, what you are interested in, what is the value of x, for that you get a null space, this is 0, right, and you can see that if you use 1 0 0, this will go to 0. So, your eigenvalues are 1 0 0, eigenvector is 1 0 0, then you will have from corresponding to u minus a, similarly you will have this, and u plus a, this will be the eigenvector. You can calculate and make an eigenvector matrix, which is basically rho minus a rho a square 1 0 0 rho a square, right. This is your eigenvector matrix capital X. Okay. Now, we will do little bit of algebraic trick. Okay. So, you know that your A is equal to x lambda x inverse, right. How you know that? So, if you write this eigenvalue matrix, okay, so this is will become, okay. So, you have this where lambda is the lambda eigenvalue matrix, which is lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, right. So, this is how your x is your eigenvector matrix, right. So, if you do x inverse, so this will become A equal to x lambda x inverse, that is one part. Similarly, you can write x inverse A x is equal to lambda. Why you are able to write it? Because you have got distinct eigenvalues and you can get the inverse. Okay, distinct eigenvalues, that means your eigenvectors are also independent and you can get the inverse, and you can write this form, right. So, use this value. So, you have this relation du by dt equal to A del by del x, replace this A by x lambda x inverse, okay, and then multiply by x inverse u, right. So, then what will happen, that this x inverse u, if you multiply, this will get cancelled out. So, you get a new matrix, which is so this x inverse u is also a vector, right. We call this vector as v. So, you got a new relation, which is dv by dt equal to lambda del by del x. Now, recall lambda is now, I mean only this is lambda 1 0 0 0 lambda 2 0 and 0 0 lambda 3, right. So, now it is a decoupled equation, right. Earlier it was coupled. If you look at the earlier equation that we had, okay, this is a coupled equation, you cannot decouple rho u and p, but now in terms of new variable which is given by v, okay, this is a decoupled equation. Okay. So, you can write it maybe dv1 by dt plus lambda 1 dv1 by dx equal to 0, dv2 by dt plus lambda 2 dv2 by dx equal to 0, and so on and so forth, lambda 3 dv3 by dx equal to 0. Okay. So, now what we learn here is that we have decoupled the equation and what are the values of v. Okay. So, let us look at here. So, if you do x inverse u, this is the value of v, this is your v. Okay. This is your new vector and you can write everything in this, and this is your u, this is your lambda, and finally, your equations will look something like this. Okay. This is your final equation. These are called the characteristic form of the Euler equation. Characteristic form of 1D Euler equations. Okay. If you go to 3D, okay, so right now we have 3 waves. Okay, we are traveling with a speed u minus a, u and u plus a. Okay, so these are basically entropy waves, acoustic waves, thermal waves, and so on and so forth. In the 3D, you will have 2 more, which are will be basically u and u. So, you will have u plus u minus a, u and u plus a. So, there will be, if it is 3D, there are 5 waves. Okay. So, what you can decouple the equations and write it. So, if you take one equation at a time, so because these are all decoupled, all these elements are 0, you can see here these are decoupled equations. So, you can write it, this is a dp by dt, and you can remove some terms. Okay. So, maybe 1 by 2 raised square. Okay. So, this will become rho a du by dt u minus a. So, this is the variable that you have, which is propagating at the speed of u minus a. Okay. Similarly, you can write for the second one, and similarly you can write for the third one. Okay, so these are three characteristic equations that we got. Okay, so in summary, if you look at these three equations, so we have a wave which is du minus dp by rho a equal to 0, which is traveling at a speed of u minus a. Okay. Similarly, this dv0, which is at corresponding to dx by dt equal to u, and this is the wave. Okay. So these are the wave speeds. Okay, and this is basically the variable which is traveling that wave speed. Okay. So there are three characteristic waves corresponding to u minus a, u and u plus a. So we'll now we have these characteristic equations. We'll look at the implication of this characteristic equation in the next class. Thank you very much.